All right, here we are. Solutions to quiz 14A. So pull it out, even if you did it. It's time to check your answers and make corrections. And hopefully everything's okay. All right, we're going to go through the solutions of all the problems. All right, Mr. Lewis, what do we got for problem number 1?
All right, we have 5 multiple choice questions, each with 4 possible answers. And we want to know the probability that if you just guessed, what's the probability you get none of the questions correct?
Oh, that would stink.
Yeah.
It's over for at least 1 or 2.
Right.
All right, so, well, we have intersection of 5 events. So the probability that the first one is incorrect
Would be 3 out of 4.
Yeah. And then, since we have 5 questions, that's to the
5th power.
5th power. Say Mr. Lewis, I'm writing. Okay, so 3/4 raised to the 5th is 0.24. 0.24.
Okay.
Wow, 24% chance that
None of them are. That's pretty high.
Wow. All right, what's probably to get all the questions correct?
Well, that would be the opposite. 1 out of 4 to the 5th power. Probably not going to be as high.
No. So as a decimal, it's 0.00098. Okay, which is
So
0.098.
not even a percent.
I just forget about that happening.
1/10 of a percent.
Okay.
chance.
All right. So those aren't complementary events, though.
No, they're not.
Because at least,
That leaves quite a bit to get to 100.
right. Okay. Let's probably get at least one of the questions wrong. So that word "at least,"
Yeah, that would probably.
especially if you're over 50,
So we're gonna
worry about your heart
We're gonna subtract.
condition.
We're gonna subtract that by the probability that we get none right, or all of them right. So we get none of them wrong.
Yeah, none wrong, which is all correct.
Right.
So it's
1 minus. We already figured that out here.
1 minus 0.00.
It's like 99%.
And you get 0.9990. Roughly. Okay. So very high chance you're going to get at least one of the questions wrong.
Yes.
Okay. Get your first incorrect answer on the 4th question.
Ooh.
So we got to get the first one right.
Yeah.
There's 1/4 chance of that. Times
I don't know why I put a comma. 1/4 times
probability of the second one, right? And the third one is to be right. And the 4th one
is wrong.
is wrong. The 5th one, we don't care about.
Right.
And we get 0.012 or a 1.2% chance that the first incorrect will be on the 4th.
Mm-hmm.
Okay. So it's all using the independence rule.
Yes.
If they're independent events, we can multiply their probabilities. All right, next.
Okay. Okay. We have a company who produces bags of peanut butter M&Ms.
Mm.
They report that they make 10% brown and red candies, 20% yellow, blue, and orange. The rest of the candies are green. So, if you pick peanut butter at random, what's the probability that it's green? Well, so we have...
First of all, I like this. You know why? Because they're only picking 1.
Yes.
We'll get to the part where they're picking 2 in a second.
So it was 10% brown, 10% red, 20% yellow, 20 blue, 20 orange. So
That's 60.
that's 80. So it looks like there's also 20% that are green.
All right.
So what's the probability of this green? 20%.
Good. Okay. Primary color, red, yellow, or blue. Those are disjoint events. So it's just common sense that you can add those.
Right.
We're using actually the second probability rule.
Red, yellow, blue. So 20, 20, and 10 gives us 50%.
Not orange.
Well, orange was 20%, so I think there's an 80% chance then that it's not orange.
And what rule did you use without even realizing it?
I don't even remember.
How'd you get the 80%?
I just said that anything was not orange, so I subtracted 100 by 20.
So that would be the complement rule.
That would be the complement rule.
Excellent.
See?
You know it or not, you're using the rules.
I know.
Okay, so we may have to go back or try to remember. This is using the same setup. If you pick 4 M&Ms in a row, what is the probability that they are all blue? I think blue was 20%, wasn't
I
it?
believe so. So 0.2, and we want to the 4th.
Which is 0.0016.
0016.
Or 0.16%.
Right.
Right, none are green. So green was 20%.
Right.
So
So
it'd be
80%. Oops. To the 4th.
so 0.8 to the 4th.
Mm-hmm.
I get about 41%, 0.41.
Okay.
Okay, at least one, or again, danger words, at least.
Right.
So
So we're going to do 1 minus probability that, none are red.
Okay, so it'd be 1 minus,
So red was 10%.
was it?
Right.
We're going to assume so.
So we get 0.9 to the 4th.
Right. I get 0.34.
Okay.
So if you like those reds, 34% chance. The 4th one is the first one that is brown. You remember percent that were brown?
Yeah, 10.
Okay. So I hope we're right about this. The 4th one is the first one is brown. So the first one's not a brown. 0.9 times 0.9 times 0.9.
Too many points. We'll make these bigger for the multiplication sign.
Okay.
Okay.
Times.
Times 0.1.
Okay, I get 0.0729.
Oh,
Point
that's
zero.
right.
0.0.
Oh, 0.073.
Or 7.3%.
Right. Sorry. Just said 0. Okay. After picking 10 in a row, I have not picked a red one.
Ah.
But your friend says you have a better chance of getting a red candy on your next pick since you have not yet seen one.
All right. This is actually a little bit more complicated answer. If it were a small bag of M&Ms, then
Yes. That would.
and each bag had the same number of reds.
Right.
We're assuming we're picking from a large bag of M&Ms.
Yeah.
So we're assuming that each time you pick an M&M, the color is independent.
Right.
So that's a little bit of an assumption, but we're assuming that 10 M&Ms out of a huge bag is not a big difference.
Right. We are assuming you still have. Oh, can't write today. 10% chance.
Right. Okay.
Mm-hmm.
That's like flipping a coin. If you flip a coin and get heads 10 times, the chances of getting heads the next time is still 50-50.
Right.
The coin doesn't remember.
Coin
So we're
and,
kind of assuming independence here. But that is an assumption.
coin and dice toss are a lot easier on that one.
All right.
All right. We have a fun little table here.
Now, there was a big typo on C, and we'll go with what it says here, but they didn't write what they meant. Okay, so C, I don't know if I'm going to circle C and I think E. Someone asked me, weren't these the same things? And the way they're worded, I have to agree with them. But it wasn't what the publisher meant. Anyway, we'll worry about that when we get there. Okay, so it says a survey in introductory statistics class in autumn 2003. That's been a while. Asked students whether or not they ate breakfast the morning of the survey, and the results are followed. So this is a two-way table. One variable is whether they ate breakfast or not. The other variable is the sex. Okay, so what is the probability that a randomly selected student is female?
Well, that would just be 199 out of the 331.
Good. We may need a decimal later, so it's 0.601. Okay, what's the probability that a randomly selected student ate breakfast?
191 out of 331, which is
0.577.
okay.
They meant to say, what is the probability that a randomly selected student was a female and ate breakfast, but they didn't say that. So the way it's worded is kind of conditional. So maybe we can write the symbol. The way it's worded is that it's what's probably that randomly selected female ate breakfast. So that's breakfast,
breakfast.
given that they're a female. I think if you, so that's not what they meant, but that's what they said. So let's do that one, what they said. So breakfast, given that they're a female. So there were 199 females and 125 ate breakfast. So 125 out of 199, and it's 0.628. All right, D. What's the probability that a randomly selected student is female given that they ate breakfast? This is the other way around.
Right. So
What's the probability of female given they ate breakfast? So that'd be 125 out of 191, which is slightly different. It's 0.654.
0.654.
Now, E, as we said, is the same thing as C. It's actually worded more clearly,
Yes.
so it's the same thing.
So this would be 0.128.
Okay, now F.
Was it? Oh, 628. I'm sorry.
Uh,
It was 628.
okay,
I just
now
can't read my own writing.
F is the million-dollar question.
Does it appear whether or not student ate breakfast independent?
So here's how we figure this out. We can use our answer to D. Right, the probability of female given breakfast.
Mm-hmm.
Could you write that?
Mm-hmm.
So we want to see if this equation is true. Female given breakfast is equal to just the probability of getting a female. So in a sense, just telling you that the person ate breakfast changed the probability that it's a female or not, or affect our knowledge of the probability. Does it matter that I tell you they had breakfast? That's what this is saying.
Mm-hmm.
Okay, so the probability of female given breakfast, we calculated in D. That was point,
6.5.
yeah, so could you write 0.654 on the underneath it? And the probability we get a female was given an A.
0.601.
So telling you that the person had breakfast affects the probability a little bit.
Slightly.
Yeah.
Yes.
But for probability, usually we want it to be exactly the same.
Right.
To be independent. So we would say, no, they're not independent. So not independent. If it didn't matter that I tell you they had breakfast, then it would be independent.
Right.
But it matters. All right.
Yes, sir.
Mr. Lewis,
Is that it?
let's see.